Hello everyone, my name is Kshitij. Today I am going to talk about the work that we did on the impact of different voltage unbalance metrics in distribution system optimization. This was work we did for a project that was funded by DOE's Solar Energy Technologies Office. So I will start by giving a brief introduction of voltage unbalance. As you all know, in the recent past there has been a growing penetration of distributed energy resources like rooftop solar PV. Now there is uncertainty associated with power injection of such resources, and typically they are not allocated equally between the three phases in the grid. So this gives rise to a power quality issue called voltage unbalance. Now in a perfectly balanced system, we have only positive sequence components. If the grid is unbalanced, then we also have negative sequence components now that are going to affect three-phase induction motors. Now these motors are predominantly the most common loads that you find in the grid, and they're also very expensive. So as you can see from the two plots here, that as the percentage of unbalance increases, the motor would have to be derated in order to avoid permanent damage, or else the losses in the machine are going to increase. Now apart from negative sequence components, we also have zero sequence components flowing in the grid. Because of this, now we have currents in the neutrals, and that can give rise to additional network losses. So the next question would be, how do we measure voltage unbalance? Interestingly, there are three most commonly used voltage unbalance definitions. The first definition is also known as the true definition of unbalance, which is endorsed by IEC standards and more commonly known as voltage unbalance factor, or VUF. So it is the ratio of negative sequence voltage component over the positive sequence voltage component. The other two definitions are approximations of the IEC's definition, and they only use voltage magnitudes and ignore the voltage angles. So the NEMA definition, or LVUR, is used by motor manufacturers, and they use the line-to-line voltage magnitudes in order to measure unbalance. The third definition, or the IEEE definition, known as PVUR, is used predominantly by electrical grid operators, and they use phase to neutral voltages in order to calculate unbalance. Now what is interesting is that these three definitions of voltage unbalance are partially inconsistent. So what this line here is trying to say is that operating points that satisfy one standard does not guarantee that they are going to satisfy the other two standards too. There are existing methods in order to mitigate voltage unbalance. One of them is to switch the residential loads between the phases and allocate them evenly, but this is done rarely in the year, and for most of the year the grid is still unbalanced. The other option would be to use transformer or regulator taps, but this requires constant switching, which might lead to failure of the equipment. The third option is to have additional energy storage devices in the grid, but this might be an expensive option. So the method that we use for this work is reactive power control of inverters. So most rooftop solar PVs are connected to the grid via inverters, which have reactive power capabilities. So since we are using existing equipment in order to minimize unbalance, there will be no additional investment cost. Moving on to the motivation and the main contributions of the work. So there has already been previous work in this area. So the inverter's active power and reactive power capabilities have been used to minimize unbalance, but the most of the literature has focused on using one definition of voltage unbalance. So different from previous work, what we try to do is have a more comprehensive approach and evaluate the impact of using different voltage unbalance definitions when we are trying to solve a three-phase optimal power flow problem. And we also look at other power quality metrics like network losses. So in order to do this, we set up the distribution system model in a phase by phase frame, and we also have the three different voltage unbalance definitions formulated as both constraints and objective functions. So moving to the other power quality metrics that we look at in our work, the first one is network losses, as I mentioned before, because they drive the cost of electricity distribution. So we calculate network losses using the voltage drop and the current flowing through all the branches in the grid. The other power quality metric we look at is the substation power factor, which is the ratio of the active power to the apparent power. So for a given active power in the system, if the power factor at the substation is low, then that means that our apparent power is high, which means the equipment at substation needs to be rated for a higher value. And this can also mean that there is more current flowing in the system, and that leads to additional network losses. So now I'll talk about the three-phase optimal power flow formulation that we have in the work. So we have two problems set up. On the left, we have minimize voltage unbalance subject to operational and physical constraints. And on the right, we have minimization of losses subject to the same set of constraints, and we also add the unbalance now as constraints instead of objective function here. It must be noted that for both of these problem formulations, we have all three voltage unbalance definitions formulations. Now we use nonlinear AC power flow equations and we set up the model in Julia, and this model has been benchmarked with GridLabD. So moving on to the distribution system modeling that is required in order to formulate the nonlinear AC power flow equations. I'll start off with distribution lines and cables. So here is an example of a simple two-bus system. So as you can see by the variables listed, we use voltage magnitudes and voltage angles, which means we set up the problem in polar coordinates. Now, because we are dealing with a three-phase unbalanced system, we cannot ignore the mutual couplings between the three phases. So the branch admittance matrix is going to look like this. It's a 3 cross 3 matrix where all the diagonals are the self-impedance values and all the off-diagonal elements are the mutual couplings. Typically, all nodes in distribution grids are not three-phase. There will be some two-phase and single-phase nodes. So in such cases, we ignore the missing phase, and then the branch admittance matrix correspondingly reduces in size. So once we have this matrix, so we can calculate the bus admittance matrix similar to the single-phase OPF, and then we use the G and the B matrices here to formulate the nonlinear power flow equations. Moving on to the next model, which is transformers. So here is a single phase equivalent model of the transformer, and the transformer admittance matrix is going to look like this. So it's a 6 cross 6 matrix with the 4 submatrices shown here. So C here is a connection matrix that maps the voltage drop across the coils to the actual node voltages that we use as variables in our OPF formulation. And YPR here looks something like this. So in order to model the transformer, we have a few assumptions. So we assume the interface coupling is 0. So that's why we only have diagonal terms and all the off-diagonal terms are zeros. The other assumption is that the self-admittance values and the mutual couplings all have similar characteristics and they're all equal to transformer leakage admittance YT. So that's why we only have ones populated in this matrix. So the voltage regulator is also modeled as a transformer. The only modification is that we now include constant tap ratios in this formulation. Moving on to the loads now. Since we have a lot of voltage dependent loads in the grid, we use the zip load model equation as shown here. So we have the constant impedance and constant current load models that depend on the base voltage VB in the system. And then of course we have the constant power load components. Another important thing to note here is that capacitor banks are modeled as constant impedance loads. Due to time constraints, I'll skip the constraints and objective function formulation and directly move on to the simulation results. So I'll start off with the IEEE 13 bus feeder as shown here on the right. So we modified this feeder in order to include 15 single phase rooftop solar PVs that are shown here by houses. So each PV inverter is rated at 50 kVA and the active power of these inverters is set to a constant value such that the total PV penetration is 35% of the rated load. Now we have 5 problem formulations that we look at. So P1 or problem 1 is where we minimize network losses in the grid and we don't really look at unbalanced constraints. So P2 to P4 is minimizing the different voltage unbalanced metrics, and then we have P5 where we minimize network losses, but now we have voltage unbalance as constraints. And all these values that you see here are the limits specified by the corresponding standards. We'll start by looking at the results for P1 loss. So on the x-axis, we have the different voltage unbalance metrics. On the y-axis, we have the unbalance in percentage. All the orange bars here are the average unbalance that you see across all three-phase nodes in the grid. All the blue bars are the maximum unbalance that you see across any single three-phase node in the grid. The green dashed line is the 2% unbalance limit specified by IEC and IEEE. So as you can see, the voltage unbalance limits are violated for P1 case where we minimize loss. Minimizing VUF reduces VUF and LVUR, but it actually considerably increases PVUR. Same is the case when we minimize LVUR. We see that these two actually show a very similar trend. So that means LVUR is actually a good approximation of VUF. Minimizing PVUR gives us the best solution in terms of unbalance. So you see none of the unbalanced metrics are close to 2%. Same is the case with P5. We see that the maximum unbalance is at 2%, which means the unbalanced constraints are actually binding for this case. Now we look at the results for the other power quality metrics. So we have all the cases on the x-axis, and we look at the network losses, substation power factor, and also look at average reactive power injections of all the 15 PV installations. So we start off with P1 loss. We see that the power factor is high and we have a positive reactive power injection. Minimizing VUF or LVUR actually increases losses and reduces the power factor at substation. This is because now we have negative reactive power injection, which means they're absorbing reactive power from the grid and the balance is now coming from the substation. Minimizing PVUR or case P5, where we minimize loss subject to constraints, unbalanced constraints, shows losses that are very similar to our base case. This is now because we have positive reactive power injections, and that is why we also have a good power factor at the substation. Now we move on to a larger taxonomic feeder. So we are looking at an 820 single phase node feeder as shown here on the right, with substation right here on top, and all the colored dots are the rooftop solar PV installations. So we run similar cases compared to the 13 bus feeder, with the only difference being the base case. So now we have a power flow run using the Newton-Raphson method, and there is no optimization involved in this case. As expected, we see that all the unbalanced limits are being violated for the base case. So minimizing unbalance using any of the three unbalanced metrics shows considerable improvement, and we see a lot of reduction in unbalance. Same is the case with P5. Here we also see a reduction in unbalance. What is different compared to the 13 bus feeder is that now the unbalance constraints are no longer binding. Now we look at results for the other power quality metrics. So the losses for the base case are very high and we have a low power factor. And since there is no optimization, the reactive power injection is 0. Minimizing any of the unbalanced metrics leads to considerable reduction in losses, but we see a drop in the power factor. This is because the average reactive power injection is negative. Moving on to case P5, we see an even further drop in the losses, and the difference now is that there is a higher power factor because we now have positive reactive power injections. So to conclude, the main goal of the work was to analyze the impact of using the different voltage unbalance definitions when we are solving a three-phase OPF problem. So in order to do this, we set up a flexible model of an unbalanced three-phase distribution grid in the phase-by-phase frame. So we saw that from the two test cases that the results were different. Some of the observations were that if we try to minimize unbalance using one definition, then we were increasing the unbalance using another definition, and in some cases the losses also increased. But what was common in both the results is that P5, the case where we minimize loss subject to unbalanced constraints, was the best option because we had low network losses and none of the unbalanced limits were violated. One of the directions for future work is to investigate more numerically efficient approaches when we are trying to solve the three-phase OPF problem and reduce the computation time for large and realistic distribution feeders. Thank you everyone for your attention.